Okay, so in today's lecture, we're going to be finishing off with L'Hopital's rule by looking at those remaining indeterminate forms that we didn't cover last time. So previously, when we looked at L'Hopital's rule, we had the limit as x goes to c, whatever that may be, of f of x over g of x, where the top and the bottom were both 0. So it was indeterminate form of type 0 over 0. Or it was an indeterminate form of type infinity over infinity. Okay, and we looked at examples with that. And at the end of the last lecture, I pointed out that there were other types of indeterminate forms. We could also use L'Hopital's rule for that, but it requires a bit more work. Okay, so let's go over what those indeterminate forms were. So indeterminate forms. Okay, so these are mathematical things that look like they may not have some specific value, but with a bit of work you can figure out what the value should be. And we looked at the first two, where we had type 0 over 0. So we had the limit where the numerator went to 0 and the denominator also went to 0. Now, you can't just say the limit doesn't exist right away. There was some more work we had to do to figure out what the value might be. Okay, sometimes there is a value, sometimes there isn't, but just because it looks like this doesn't mean you can't find the value. Okay, number 2, we had infinity over infinity, and again, you can't just say the limit doesn't exist just because the top and the bottom are both infinity. We can use L'Hopital's rule to figure out what the value should be. Okay, and we looked at these two types, and we did a few examples on that. Today, we're going to look at the remaining types, and we've got 6 examples that cover those types. Okay, so number 3, we have type 0 times infinity. So this is when we have a limit of a product where one of them ends up being 0 and the other ends up being infinity. Now, you can't say 0 times infinity. That doesn't mean anything. So this is an indeterminate form. And again, we have to do some more work to figure out what the limit value should be. Okay, and then number 4, we have infinity minus infinity. This is another type of indeterminate form where the first value gets very large, the second value also gets very large. So individually, they go to infinity, but if you take the difference, it might be something, or it might not be. It depends on the problem. And we'll see our first example will be on this type. So if you just look at the first part of the limit, you say it's infinity. The second part of the limit is also infinity. What kind of value do you give to that? Okay, so these are the things that you need to look out for. Number 5, 0 to the 0. Okay, this is also an indeterminate form. Just looking at this, we can't give it a value. Is it 0? Is it 1? You can't tell. And we'll see examples on this as well. Number 6, 1 to the infinity. Okay, we'll see things like this. And when we say 1, we're referring to the limit. So if we have 1 plus a very small amount to the power infinity, then that goes to infinity. But as we get closer and closer to 1, it's a bit uncertain on what that needs to be. Okay, and you can check that on your calculators. Put 1 to some very big number, put 1.01 to some big number, and you'll see it will diverge. Okay, and lastly, number 7, infinity to the power 0. Okay, and again, you can put this on your calculator for a few values. Put a very large value as the base, put a very small value as the exponent, and if you change those a little bit, you'll see the value can change quite a lot. Okay, that's what we mean by indeterminate. You can't see clearly what the value will be. Okay, you need to do more work. Okay, so these 7 are the types of indeterminate forms that you need to look out for when evaluating a limit. So if you just naively try and evaluate the limit and you get one of these 7, that's a big hint that you should use L'Hopital's rule. Okay, not always. Maybe there's another method that's easier, but if you do end up with one of these 7, L'Hopital's rule is a good start. Okay. Okay, let's have a look at some examples with these, and I'll show you how to spot which one it should be. Okay, so number 1, we have the limits as x goes to 1 of x over x minus 1 minus 1 over the natural log of x. Okay, so here we've got the difference of two things. Now remember your limit laws. You can have the limit of the first thing minus the limit of the second thing, provided both limits exist. Okay, remember we had the whole list of limit laws, and there was a big exclamation mark saying if both limits exist. Here, we can't split it up into 2 parts. If we look at the first part just by itself, we have x over x minus 1. If x goes to 1, the bottom is going to go to 0. So we have a 1 over 0 there. That's going to be infinite. And that doesn't work out nicely. And if we look at the second one, we have the same thing. We have the natural log of x. When x goes to 1, that's going to go to 0. And again, we have 1 over 0. So the first part goes to infinity. The second part goes to infinity. So we see its type 4. Okay. Just looking at the 2 parts of the limit, we can't tell what the value should be. The first is infinity. The second is infinity. How do we subtract them? We can't. So we need to do something else. Okay. The first step is to combine these 2 into one fraction. With them being 2 fractions, we get infinity minus infinity. It doesn't work. If we combine it into one fraction, it might be easier to work with. So let's do that. So here we have the limit, x goes to 1. How do we combine fractions? We need to find the common denominator. So cross multiplying, we get x ln x minus x minus 1 all over x minus 1 ln x. Okay, so we've combined it. Maybe this fixes the problem. Maybe it doesn't. Let's have a look. In the top, when x goes to 1, the natural log will be 0. X minus 1 will be 0, so the top is 0. In the bottom, x minus 1, that's going to be 0. So now we have 0 over 0. That's the first type of indeterminate form we looked at. And we can use L'Hopital's rule. If it's 0 over 0 or infinity over infinity, we can use L'Hopital's rule. So let's do that. So we're going to use L'Hopital's rule, which means we need to take the derivative of the top and the bottom and then check if the limit gives us anything. So derivative of the top, x ln x, that's a product of 2 things. We need to use the product rule. Okay, we differentiate the first term. That's just 1, so we end up with ln x. Plus, now for the second part, we differentiate ln x, that's going to be 1 over x, but times the x, so that's going to be plus 1. Minus x plus 1, the 1 goes away, so the derivative of minus x, that's minus 1. Okay, so that's the derivative of the top taken care of. Okay, now the derivative of the bottom. We take the derivative of the first term, that's just going to be a 1, times ln x, plus, now we leave the first one alone and then take the derivative of the second, so that's going to be x minus 1, and then we have 1 over x there. Okay. Things work out nicely in the top. The 1 and the minus 1, they go away, so we can cancel that. So this is going to be the limit as x goes to 1, the natural log of x over the natural log of x, plus, and then we have x minus 1 over x. Okay, let's see what happens again if we substitute 1. In the top, we have the natural log of 1, that's going to be 0. In the bottom, we have the natural log of 1, that's also 0. And then 1 minus 1 over 1, at that bit over there, that's also going to be 0. So we still have type 0 over 0. Okay. which means we can use L'Hopital's rule again, right? We've got type 0 over 0. We can differentiate. We can use L'Hopital's rule. So let's do that. In the bottom, just before we do L'Hopital's rule, I just want to expand the bottom out a bit. So that's going to be ln x over ln x plus the x over x, we can put that as a 1. Okay, and then the minus 1 over x, we can put that separately. Okay, that just saves us from worrying about the quotient rule. Okay, so now we can use L'Hopital's rule. So we have the limit as x goes to 1. The derivative of the top, that's going to be 1 over x. Okay, we know that from our inverse functions. In the bottom, we have the derivative of ln x, that's also 1 over x. Okay, plus 1, that goes away. The derivative of minus 1 over x, that's going to be 1 over x squared. Okay, good. Okay, now what happens if we substitute 1? Do we still have a problem? In the top, we have 1 over 1, that's just 1. Nothing wrong with that. In the bottom, we have 1 over 1 plus another 1 over 1. No problems there. So we have a 1 at the top, we have a 2 at the bottom, so it's just a half. Okay, at this point, when we can directly substitute, then we're fine. We don't have to worry about anything anymore. Okay, everything's nice and continuous. You can just substitute 1 and you get your answer. If you substituted 1 and you still got 0 over 0, then you do L'Hopital's rule again. Okay, so maybe you do it once, maybe you do it twice, maybe 3 times. You just keep going until you get something where you can substitute. Okay, there's no more problems at this step, so we just substitute. Okay, any questions about this one? Okay, so if you have infinity minus infinity with like 2 fractions like this, it's best to make it a single fraction. Once you have it as a single fraction, you can then test for L'Hopital's rule. Like your f over g. If it's f minus g, you can't use L'Hopital's rule. That doesn't work. Okay, so make sure you get it into a single fraction and then do L'Hopital's rule. Okay, any questions on this one? No questions. Okay, let's have a look at the next example. Okay, so here we have the limits as x goes to 0 of x ln x. Okay, first step, you substitute and see what happens. For the first bit of the product, when x goes to 0 of x, that's just going to be 0. The natural log of x when x goes to 0, that's going to be minus infinity. That's infinite. So we see we have a type 0 times infinity. So we have an indeterminate form. So we can try use L'Hopital's rule, but we can't use L'Hopital's rule in this form. We need to change it. So instead of 0 times infinity, we need to make it 0 over 0 or infinity over infinity. Okay, now how do we do that? We can do that with the following trick. So we have the limit, x goes to 0, natural log of x. Instead of multiplying by x, I'm going to divide by 1 over x. Okay, so think of it like instead of multiplying by 2, you can divide by a half. Same thing. So we haven't changed anything, but now what type of indeterminate form is this? In the top, when we have x goes to 0, the top will be infinite. In the bottom, we have 1 over x. When x goes to 0, that's also infinite. So now we have infinity over infinity. And since it's infinity over infinity, we can now use L'Hopital's rule. So in line 1, we couldn't use L'Hopital's rule because it's 0 times infinity. We just change it slightly. Now it's infinity over infinity, and we can use L'Hopital's rule. Okay, so just make a little note. Can't use L'Hopital's rule, right? Because it's infinity times 0. That doesn't work with L'Hopital's rule. Infinity over infinity, now we can use L'Hopital's rule. Okay, Remember those conditions for L'Hopital's rule. The first condition was it has to be 0 over 0 or infinity over infinity. Infinity times 0 doesn't work. We need to change it a bit first. Okay, but now we can use L'Hopital's rule. Let's do that. We take the derivative of the top and the derivative of the bottom. So we have the limits x goes to 0. The derivative of the top is just going to be 1 over x. Derivative of the bottom minus 1 over x squared. Okay, we've got a fraction over a fraction. Please be careful with these. Okay, when you've got fractions over fractions, don't mess up, what goes where. So here we can rewrite this as the limit x goes to 0 minus x squared over x. If you divide by a fraction, that's the same thing as multiplying by the reciprocal. For example, if you have 1 over a divided by b, that's b over a. You swap it when you divide by that fraction. So here we're dividing by minus 1 over x squared, so that's the same thing as timesing by minus x squared. So we put it at the top. Sorry, you got a question? Why are you talking? Okay. Now, x squared over x. Just looking at this, you might think it's a problem because the top is 0 and the bottom is 0, but we can simplify first. So this is going to be the limit as x goes to 0 of just minus x. Okay. So whenever you can simplify, simplify. Okay. Don't just leave it like x squared over x. Make sure you simplify. Because we see that x squared over x, that's 0 over 0, it's a problem. But we can just write minus x. And now it's much easier to work with. Now this is just 0. Okay. Once we get to that last step where we can just substitute, then we just substitute. And we've got our answer. Okay. No more work needed from there. Okay. Any questions on this one? No questions. Okay. So again, we've got 0 times infinity. It's an indeterminate form. So we can use L'Hopital's rule, but only if we change it to type infinity over infinity or 0 over 0. Here we could make it infinity over infinity with a little reworking of x. Okay, please make sure you do that step before you consider L'Hopital's rule. Okay, it must be something like this. Okay, or 0 over 0. Both work. Okay, any questions on this one? Yes. Yeah, so we're taking the x, and instead of multiplying by x, we're dividing by 1 over x. Like multiplying by 2 is the same thing as dividing by a half. So we just took it to the denominator, but it has to be 1 over that. Okay, like this over here. So 1 over a divided by b is b divided by a. You can swap them. Okay. You could think of this as x over 1. And then it becomes 1 over x in the bottom. Okay, yeah. So if you want to write it as x over 1 and then 1 over x, that might help. Okay, if you don't see that right away. So the x over 1 becomes 1 over x because we swap. Okay. Let's have a look at number 3. So here we have the limit as x goes to 0 of x to the x. Okay. Now, what happens when x goes to 0? The base is going to be 0, and the exponent is going to be 0. We see over here, that's type number 5. Okay, 0 to the 0. So it's an indeterminate form. So we want to use L'Hopital's rule, but we can't use it in this form. 0 to the 0 doesn't work. It must be 0 divided by 0 or infinity divided by infinity. So we have to do something. And what we can do, let's do a different color over here. If you have some function and the exponent is also a function. Okay, so x is just by itself, but it's still a function. It's like f of x equals x. what we want to do is bring it down. We don't want it in the exponent. Okay, it's easier if we work with it being multiplied. So how do we take something from the exponent, bring it down? Log. Yeah, so if we have the log of a to the b, this is equal to b log a. Okay, that's what we're going to be using here. Since we've got a function to another function in the exponent, we can use logs to bring it down, so we don't have to work with the exponent. So what we do is we call this limit L for limit, and we're going to take the log on both sides. Okay, now we can't take the exponent down immediately. There's a few steps we have to do before that, but that's the idea. We take the log on both sides, and that exponent will then come down. So the natural log of L is equal to the natural log of the limit as x goes to 0, x to the x. Okay, so I just took the log on both sides. That's fine. If you have an equation, if you do something to the one side and you do the same thing to the other side, everything's fine. Now, what we're going to use here is the fact that the natural log is continuous. Okay, the log function is continuous, which means the limit can go inside or outside the function. Okay, please look back at your notes on continuity if that's not clear to you. So this limit, we can take it inside or outside the function because the natural log is continuous. Again, if that's confusing, please go back to your definition of continuity. Okay, so this becomes the natural log of L is equal to the limit as x goes to 0, the natural log of x to the x. Okay. Now that the natural log is inside the limit, we can apply it to x to the x. So the x will come down. So this is going to be the natural log of L, limit x goes to 0, and this is just going to be x ln x. Okay, which we saw in number 2. Okay, so we know how to do that one. So if we just go back here, okay, this x ln x, we got an answer of 0. So here, this will also be 0. Okay, but the limit is not 0. The natural log of the limit is 0. We still want L. So we exponentiate both sides. So e to the natural log of L is e to the 0. So L is 1. Okay, so e to the 0, that's just 1. E and the natural log, they cancel because they're inverses. So we get L is 1. Okay, and that's our limit value. Okay, so whenever we have some function to the power of some other function, we can use this natural log trick to bring the function down. Okay, it's difficult to work with it being in the exponent, but if they're multiplied, it's a lot easier to work with. Like in this case, it's much easier to work with x ln x instead of x to the x. Okay, any questions on this one? Yes. Yeah, we've got a few more to go through. Okay, any other questions? Everyone's good with that. So you have some function to the power of some function. You can use the natural log to bring the function down. Okay, number 4. So very similar, we're going to have the limit as x goes to infinity of 1 minus 1 over x to the x. And again, we've got this function to the power of a function. So we're going to use that natural log trick that we learned. Okay, so firstly, what type of indeterminate form is this? It might not be, but we can check. When x goes to infinity, 1 over x is going to go to 0. So the base is going to be 1. And the exponent is going to be infinity. We go back to the page here. That's going to be type 6, 1 to the infinity. So yes, this is an indeterminate form, 1 to the infinity. It's not the one we want. We want 0 over 0 or infinity over infinity. So we're going to have to do some work to get there. Okay, so again, since it's a function to a function, we can use that log trick. So this is L. Taking the log on both sides, we have the log of L is going to be the limit as x goes to infinity, x ln 1 minus 1 over x. So we've turned the exponentiation into now a product. And products are a lot easier to work with. Okay, let's see what type of indeterminate form we have now. So x is going to infinity. So x in the front there, that's going to be infinite. What about the natural log? The 1 over x is going to go to 0. The natural log of 1 is 0. So we have infinity times 0. So this is still an indeterminate form. It's changed to type 3 now. Okay, so what can we do with those type 3 ones? Something very similar to what we did for question 2. We're going to change this x, or if you want to write it as x over 1, to being divided by 1 over x. So the x over 1 in front, we now divide by 1 over x. So the natural log of L, that's the limit as x goes to infinity. The natural log 1 minus 1 over x, that can stay. Now the x over 1 becomes a 1 over x. Okay, what happens now if we take the limit? In the natural log, we have the 1 over x, that's going to go to 0. The natural log of 1 is 0, so the top is 0. In the bottom, 1 over x. When x goes to infinity, 1 over x goes to 0. Okay, so we have 0 over 0. We can use L'Hopital's rule now. Okay, so the natural log of L using L'Hopital's rule is going to be the limit as x goes to infinity. And now we can take the derivative of the top and the bottom. Now we need to be a bit careful. We've got a composition there. It's the natural log of some stuff. So it's going to be a two-step process because of the chain rule. First, we differentiate the natural log. That's 1 over the stuff inside. So it's going to be 1 over the stuff inside. So we just leave it like that. Now, times the derivative of the stuff inside, right, from the chain rule. So the derivative of 1 over x, that's minus 1 over x squared. The minus and the minus make a plus, so it's 1 over x squared. Okay, what about the bottom? The derivative of 1 over x is minus 1 over x squared. Okay, now this looks really messy, but notice in the top we have 1 over x squared. In the bottom we also have 1 over x squared. They can just cancel. So now we have the natural log of L is equal to the limit as x goes to infinity. The bottom had the minus, so let's put the minus there. So minus 1 over 1 minus 1 over x. And now we see that if we take the limit, then there's no more problems. Because the top, that's just minus 1. In the bottom, 1 over x, that's going to go to 0. But we still have the 1. So it's just minus 1 over 1, or just minus 1. Okay, again, that's not our limit value. That's the log of the limit value. If we want L back, we need to exponentiate both sides. So L will be e to the minus 1. Okay, please don't forget the last step. After all of the working with the natural log of L, we still want L. So you need to exponentiate that result that we got there. Okay, and also please remember your chain rule. Okay, over here, we had to use the chain rule in the top. Okay, please don't just write 1 over 1 minus 1 over x and then forget the derivative of the inside. Okay, remember it's f prime of g of x times g prime of x. Don't forget that g prime step. Okay, yeah, there's a lot of students in the tutorial that's missed those chain rule bits. Okay, any questions? Everyone good? Okay, let's have a look at the next one, number 5. Number 5. So here we have the limits as x goes to 0 of x over 1 plus x to the x. Okay, so again, we've got this function to the power of another function. So we're going to have to use the log trick again. Okay, let's see what type of indeterminate form this is. In the brackets, we're going to have 0 over 1. So the base is going to be 0. The exponent is going to be 0. So this is an indeterminate form, number 5, 0 to the power 0. So it's an indeterminate form. We would like to use L'Hopital's rule, but we can't because it's 0 to the 0. Once we've done that log trick, we can then make some progress. So let's call this L and take the log on both sides again. So the natural log of L is equal to the limit as x goes to 0 of x, because we can take the x down now, and then it will be the natural log of x over 1 plus x. Okay. What do we have here now? So in the front we have an x with x going to 0, so it's just 0. Times the natural log, we're going to have a 0 over 1, so that's 0. The natural log of 0, that's going to be minus infinity, so we have type 0 times infinity. Okay, so we've changed the indeterminate form, but we still can't use L'Hopital's rule. It's still not 0 over 0 or infinity over infinity. But the x in front, we can write as x over 1. And then we can put it in the denominator. So the natural log of L is equal to the limits as x goes to 0, the natural log x over 1 plus x over 1 over x. The x over 1 became 1 over x. Okay, let's see what happens now. In the top, if we take the limit as x goes to 0, we're going to have the natural log of 0, that's infinite. In the bottom, when x goes to 0, that's also infinite. So this is type infinity over infinity. Now we can use L'Hopital's rule. It's the correct indeterminate form. Okay, so let's use L'Hopital's rule. Natural log of L using L'Hopital's rule is equal to the limit as x goes to 0. So we need to do the derivative of the top and the derivative of the bottom. So the derivative of the top is going to be 1 over the stuff inside. So it will be 1 over x over 1 plus x. So this is all in the top still. Times the derivative of the inside part. Now, we don't want to get this too messy, so let's write this as d by dx x over 1 plus x. Okay, we'll save that for a later step. In the bottom, we can take the derivative. That's going to be minus 1 over x squared. Okay. Now we can make things a little bit simpler. This 1 over the fraction, we can swap the fraction to make it a bit easier to work with. So we have the natural log of L is the limit as x goes to 0. We can swap the fraction, so it will be 1 plus x over x. So 1 over the fraction, we just swap it. Okay, times, we can do this derivative later. Let's leave it there. Okay, and then dividing by minus 1 over x squared, that's the same thing as timesing by minus x squared. So we can times this by minus x squared. Okay. We can make things a bit more simpler. The minus x squared over the x, that will just be a minus x. So the natural log of L, that will be the limits as x goes to 0 of minus x 1 plus x. And then we still have this derivative to worry about here. Okay, but that's fine. We can work with that. It's a quotient, so we're going to have to use the quotient rule. That's not so bad because it's just x over 1 plus x. Not too much to worry about there. So that's going to be the natural log of L, the limit as x goes to 0, minus x, 1 plus x. Okay, and let's do this with the quotient rule now. So we've got x divided by 1 plus x. So that's going to be f g prime minus g prime f over g squared. Okay, and that's really easy to do. So it's going to be f g prime minus g prime f all over that squared. Okay. Okay, so we end up with something like that. We don't even have to worry about the limits. If you put in 0, the x in the front there is going to make it 0 immediately, so the whole thing's just 0. And if the natural log is 0, that means our limit is 1. Okay, please don't forget that last step. I'm not interested in the natural log of L, I want L. So please make sure that you undo that logarithm at the end. Okay, so just a note here. We don't want natural log of L, we want L. Okay, please don't lose easy marks by forgetting the last step. Okay, any questions on this one? Okay, so very similar to questions 3 and 4. You've got some function in the bottom, some function in the exponent. We can use that log trick to bring the function down. Okay, last one for today. Number 6. We have the limit as x goes to infinity of x sine 1 over x. Okay. So we want to try use L'Hopital's rule for this one. So if we just see what happens when x goes to infinity, what happens? When x goes to infinity, the first bit there is going to be infinity times. Sine is continuous. We can take the limits inside. The 1 over x, that's going to go to 0. Sine of 0 is 0. So we have infinity times 0. So this is an indeterminate form. Let's see, it was this number 3, 0 times infinity. Okay, which means we can use L'Hopital's rule, but not in this form. We need to change it a bit first. How do we do that? Well, the x over there is going to go to infinity, and the sine is going to go to 0. So let's write this as x over 1. And then instead of having times x over 1, we divide by 1 over x. So this is the limit as x goes to infinity, sine of 1 over x over 1 over x. Okay, so let's see what happens now with the limit. Again, in the top, the sine function is continuous. The limit can go inside. So 1 over x goes to 0, which means we have sine of 0, which is 0. So the top is 0. In the bottom, x goes to infinity, 1 over x goes to 0. Okay, 0 over 0, we can use L'Hopital's rule. So let's do that. So this is equal to the limit as x goes to infinity. Now we need to take the derivative of the top and the bottom. Derivative of the top, we're going to have to use the chain rule because it's a composition. The derivative of sine is cosine times, please don't forget the inside part, the derivative of 1 over x is minus 1 over x squared. And in the bottom, we have the derivative of 1 over x minus 1 over x squared again. But that's nice, they can just go away. Okay. So, how do we evaluate this limit? Quite easily. We know that cosine is continuous, which means the limit can jump inside. So this is going to be cos limit x goes to infinity, 1 over x, y, since cos is continuous. If a function is continuous, the limit can go inside or outside, depending on what you want to do. Okay, but now the inside limit, that's easy to do. Limit as x goes to infinity, 1 over x, that's just 0. And cos of 0, that's just 1. Okay. Please don't forget these steps here with the limit going inside and outside. Okay, so just with the limit on the outside, in the previous thing there, you might think, no, you can't do the limit. But remember, cos is continuous. If we take the limit inside, the limit of 1 over x is easy. That's just 0. Okay, so remember, when functions are continuous, the limits can jump inside and out, depending on what you want to do. Okay, so we just get 1. Okay. Any questions on this one? So everyone's fine with that. Okay, so there won't be any homework for today. All of that will be in your tutorial 7 that's been uploaded now. So the LHopitals rule stuff that we covered today and the stuff that we covered previously with that infinity over infinity, all of that is in tutorial 7. Okay. And that's due for next Tuesday, as usual. Okay, then the quiz for the Tuesday, it will be on the implicit differentiation, finding derivative of inverse functions, and this LHopitals rule stuff. Okay, up to what we did today. Okay, so this new indeterminate form stuff, that will come out as well. Okay. Okay, so that's it for the LHopitals rule stuff. Tomorrow we're going to be starting on the new chapter on optimization. Okay, it's a fairly big chapter. It uses a lot of derivatives, chain rule, product rule, all that stuff. So please go over that if you need to for optimization tomorrow. Okay, that won't be in the quiz. The quiz is only up to this stuff here. Optimization, that will be in the following quiz. Okay, and for the test. Okay, the test will end at optimization.